Okay, hello everyone. So in today's video, we're going to be discussing Bernoulli's differential equation, which is really just any differential equation of this form here, where the n can be any number except 0 or 1. And you may be asking, well, this looks quite close to a first order linear equation, so what's the difference? And the difference really is just this y to the n term, because if it didn't appear, if it wasn't here, we would have exactly a first order linear equation in what's called standard form. Okay, so this is Bernoulli's equation, and luckily we have a very, there's one trick to solve them all here, and that is a very clever substitution, which is to say we make u equal to y to the 1 minus n. And the effect that this will have on the differential equation is that it will make it linear. And why is that valuable? Because we can solve linear differential equations. So if we can transform any such equation by substitution into a linear one, and we can solve every linear equation, then effectively we can solve any Bernoulli equation. Okay, so let's illustrate this technique on an example. So here we are given an initial value problem, where the differential equation here is a Bernoulli differential equation, and here we are given some initial values. Okay, so the first thing to do is to just recognize that this is a Bernoulli differential equation. So it's of the form that was mentioned earlier, and here it's easy to see that that's the case. And the only thing we really need to identify is what is n. Okay, so now that we know that it's a Bernoulli differential equation, what we want to do is to make the correct substitution. So here we're going to make u equal to y to the 1 minus n. And if n is 2, then this is going to tell us that u is equal to just 1 over y. So that y is equal to just 1 over u. Okay, so once we've made our substitution, what is our goal? Our goal is to take this whole equation and transform it into an equation involving only u's, right? So that means we need an expression for u, for y, for y and for y squared, and also for the derivative dy dx. So we have what is y, and that means, of course, we have what is y squared. So the only thing left to do is to find out what is dy dx. So if we compute dy dx, let's just remember that via the chain rule, this is the same thing as dy du times du dx. Okay? All right, and that means, so here this just means differentiate as you normally would. And here we'll just get negative 1 over u squared, and then we just multiply by du dx. Okay, so once we've done this, we're in a position to make the substitution. And we'll get the following equation. So we're going to first write this dy dx in terms of u. So we get negative 1 over u squared times du dx plus y, which is just 1 over u, is equal to y squared, which is just 1 over u squared. All right, now it's not immediately clear that this is a first order linear equation. So how to see that it is? Well, there is sort of a general thing that's always going to happen here. There's always going to be some coefficient here, which we can just get rid of by multiplying by its reciprocal. So we want to get rid of this coefficient, and the only way to legitimately do that in this case is to just multiply by negative u squared. So then we're just going to get du dx minus u is equal to negative 1. Okay, great. And now here, this is an equation which is linear. This is a linear equation. So we can just solve it as a linear equation. In fact, this is a separable equation. It's even better. So we can just quickly solve this. Du dx is equal to u minus 1. And so this implies that 1 over u minus 1 du is equal to dx. So we can integrate both sides, and we get the following expression. Just x plus c. And here we can use the inverse relationship between natural log and exponential and just get that the absolute value of u minus 1 is equal to e to the x plus c. Okay, good. Now just a bit of logic here. We have that the absolute value of a number is equal to a positive number. And now there's only really one way that this could have, there's only really two ways that this could have happened. And that is that u plus 1, the argument of the absolute value, is either equal to x e to the x plus c, or it's equal to the negative. And those are your two options only. Okay, now here, let's rewrite our equation in terms of y. So u is equal to 1 over y, so we have this. So we have these two possibilities for what our y could satisfy. And now the question is which one? And the way to determine which one we're going to use is to use the initial values. So let's take our, let's remember what are our initial values. Our initial values here are going to be just y of 0 is equal to a half, right? Now let's see, if I plug that into this equation here, what's going to happen? I'm going to get 1 over a half, so y of 0 will be a half, minus 1 is equal to negative e to the 0 plus c, which is just c. Now, okay, let's just think about this. This here is going to be, okay, so 1 divided by a half is 2, minus 1 is 1, is equal to negative e to the c. And this is problematic. This is an issue because e to the c is always positive, so negative e to the c is always negative. And here we have a negative number equal to a positive number, which is bad. So what does this mean? This means that if y satisfies our initial values, then it's definitely not of this form. So we can exclude it completely. Okay, so that means that our y here is going to satisfy just one. So I'm just going to do this quickly. Plugging in initial values here, we'll get 1 is equal to e to the 0 plus c, which is this. And this is just going to give us that c is equal to 0. So that finally, 1 over y is equal to minus 1, sorry, is equal to e to the x. And so we can just get that y here is equal to 1 over e to the x plus 1. And this can be our final solution. Okay, let's just do one more example to solidify the technique here. So let's solve this equation and see which kinds of functions satisfy this differential equation here. All right, so the first thing to do is to recognize this as a Bernoulli differential equation. So let's just let's rewrite the equation, right? So we're going to just rewrite the equation a little bit and have dy dx plus xy is equal to x divided by y here. But here, this is just the same thing as x times y inverse, right? And so this is a Bernoulli differential equation with n equal to negative 1. Okay, good. So Bernoulli differential equation with n equal to negative 1. So we make the substitution u equal to y to the 1 minus n, which is in this case just going to be y squared. Okay, so we have u is equal to y squared, and so this gives us that y is equal to square root u. And this means that dy dx, so just as we were in the previous example, we had to solve for what is y and also what is the derivative of y with respect to x in terms of u. We have to do the same here. So it's going to be, again, du dx times, dy du times du dx, which in this case is just going to be 1 over 2 root u times du dx. Okay, great. So here we have computed dy dx in terms of du only, and also we know what u is in terms of u only. So we can rewrite our equation, so we can make our substitution and get the following differential equation. So dy dx, we get 1 over 2 square root u times du dx plus x y, so plus x times square root u, because u is equal to square root u, is equal to x over y, so x over square root u. Okay, good. Again, this is not immediately clear that this is a first order linear equation, so what do? We need to get rid of this this coefficient here, and again the only legal way to do this is to multiply by 2 root u here in this case. So what we'll get is just du dx plus 2xu is equal to 2x. Okay. So this is the equation now. So we have reduced our original differential equation into this one, which is separable, and now we can solve it as a separable equation. So let me just rewrite this again. Du dx here is equal to 2x times 1 minus u, just taking the 2xu over to one side and factoring out the 2x. And this just gives us that the 1 over 1 minus u du is equal to 2x dx. And here we get natural. Okay, this is a little bit careful here. We're integrating this, and remember there's a negative u here. So the integral here is just going to be natural log absolute value 1 minus u, and that must be equal to x squared plus negative, sorry, I forgot the negative again, negative x squared plus c. Okay, and just to rewrite this without the negative in front of the natural log, this is natural log 1 minus u is equal to c minus x squared. Okay, because if I multiply this expression here by negative 1, all I'm going to be doing is adding negative x squared to an arbitrary constant again. So the c is unaffected by multiplication by any non-zero number. Okay, so we're close to the end here, because now we can just again use the inverse relationship between log and exponential and get 1 minus u is equal to c minus e to the c minus x squared. So we have this. And again, we reason as earlier. There's only 2 ways that this could have happened. That 1 minus u is equal to e to the c minus x squared, or 1 minus u is equal to negative e to the c minus x squared. Those are your 2 options. Okay, now let's write everything in terms of y, because we're in a position to do that. So we have 1 minus, so u is equal to y squared, if I remember. Yes, u is equal to y squared. Good, so u is equal to y squared, so we have 1 minus y squared is equal to e to the c minus x squared, or 1 minus y squared is equal to negative e to the c minus x squared. And again, these are the only 2 options. If y satisfies our differential equation, this is what y should look like. And again, the question is, which one? Which of these is the one that we'll be using? Let's take a look here at the first option. If I take my initial values, which I remember are going to be y of 0 equal to square root 2, and I plug them into this equation, I'm going to get 1 minus square root 2 squared, which is just 1 minus 2, is equal to e to the c minus x squared, which is just e to the c. And again, here we have the same problem as earlier. This is a negative number is equal to a positive number, which is a contradiction. This is impossible. So what we can do, because of this over here, is completely rule out this possibility. And that means that our final solution must be of this form, given by the side here. And if I just plug in the initial values here, I'm just going to get, again, so 1 minus 2 is equal to negative e to the c. And this will just mean that negative 1 is equal to negative e to the c. So that c is equal to 0. Okay, and that gives us our final solution, because now we can write 1 minus y squared is equal to negative e to the negative x squared. And here we can just solve for y and get y squared is just equal to 1 plus e to the negative x squared. And so here we get y is equal to square root 1 plus e to the negative x squared. Okay, good. So you may be saying, well, what about, there's two possibilities, right? Because we are going to have this plus minus story. So y, yeah, that's true. Y could have been also the negative. But what's the problem with it being the negative is, again, the initial values. If I plug in y equal to 0, I must get square root 2 positive. And there's no way to get that from this. This is always going to be a negative number. Good. So y is then of this form here. Okay. Thank you.